It's one of the most striking buildings in the world and home to some of the most important modern art.
It has been hailed as the greatest building of our time.
The Guggenheim Museum in Bilbao, Spain. Engineers said the futuristic design could not be built. Yet this gleaming jewel changed architecture forever and single-handedly reinvented Bilbao as an international tourism hotspot.
This spectacular masterpiece owes its success to some surprising engineering connections.
A trundle wheel.
It's like visiting a very futuristic dentist.
Sir Walter Raleigh.
I'm standing by for a huge gush of water to sink my boat.
An egg.
Definitely real eggs.
A Russian submarine.
It's gone, it's just blown clean off.
And a volcano.
I'm going to find out just how hot it is.
In the late 1980s, Bilbao was a grimy manufacturing city, struggling as its steel and shipping industries were collapsing. But the local government had a plan to reinvent the city as a hub of tourism and culture. Coincidentally, the prestigious Guggenheim Foundation decided to open one of its world-famous art galleries in Europe. The deal was made.
They decided that if they were going to build an art gallery to exhibit some of the world's greatest contemporary artists, it should be a work of art in its own right.
It was to be the centerpiece for Bilbao's reinvention, one of the first in a new generation of iconic buildings, to rival the Sydney Opera House or Eiffel Tower. Innovative, radical, shocking even. Architect Frank Gehry's designs were striking, to say the least.
This is one of his original sketches. And yeah, it doesn't look much like the real thing, but that's why Gehry got the job. He's famous for his outlandish designs. Bilbao wanted an icon, and the Guggenheim was to be it. But turning this into that was going to require technology never before applied to architecture.
Gehry's design called for delicate, complex, curved walls, and the Guggenheim Foundation wanted huge exhibition spaces. To achieve both, the walls had to be thin. But this created the first problem.
The structural engineers faced the problem of ensuring the building was strong enough to support itself.
Concrete would have worked, but the walls would have been too thick. So the engineers decided to use a thin steel skeleton. But how could they be sure that the delicate framework would be strong enough to support the entire building?
The answer is in the shape. An example, if I just hold this piece of paper out, well, clearly it's not very stiff and strong at all. But if I change its shape, put a curve in it, suddenly it's a lot stiffer and a lot stronger.
So, changing the shape of a material by adding a curve makes it stronger. And just like this art, the Guggenheim is all curves, which led to a surprising suggestion.
The engineers quickly realized that they could turn the curved walls to their advantage by making them support the building and, in the process, create huge open gallery spaces. In fact, the engineers asked Gehry to make the curves even more pronounced, even more curvy. It's not often that an architect is asked to be even more outlandish by the engineers. The secret of the Guggenheim's strength comes from an egg and a very special dam. Eggshell is famously fragile stuff. I mean, look, it just crumbles. But as it turns out, chickens are perhaps better engineers than we've ever given them credit, because if you form eggshell into the right shape, it's capable of withstanding some pretty amazing forces, as I shall now demonstrate with this experiment.
Between these two sheets of plastic, there are 384 eggs glued in place with silicone.
These eggs are not hard-boiled, they're just as the chicken provided them. All we need now is a weight, something heavy.
This will be perfect. Weighs about 3/4 of a ton, maybe. Only problem is, it's just needs to be a bit more manageable. But that's okay. A few modifications, we can achieve that. Take it away. Quite rugged and rigorous modifications, but they'll do the job.
I'm not just crushing the car for fun, although it is fun. The car is going to be the load for my experiment. By compacting it, I'm distributing the weight more evenly.
Modifying cars, very fashionable with young people.
Yep, there you go. Modified.
Here to get things cracking is a man who knows all about curves, structural engineer Dr. Aimer Waddy.
Yeah, you'd probably guess we're going to put the car on the eggs. Well, that's the theory, Aimer.
Yep.
How much difference can a shape make? I mean, how can an egg support a car?
Well, they are weak in one direction. Let's say if we loaded it like this, on my index finger and my thumb, then we have one principal direction with a very, very weak curvature, which is almost flat, so it's almost a single curve. If we load it, however, on this way with the crown, then we have a very strong double curvature of equal amount in that direction.
To support the car, the weight has to be transmitted around the eggshell to the ground. The double curve allows the forces to flow evenly around a symmetrical shape. When the egg's on its side, the forces have to travel on a less direct path and around a shape that's not symmetrical, so the forces flow unevenly. This makes the egg weaker. The deeper the curve, the more vertical and so more direct the path is to the base, making it strong.
So it's those curves that give it the strength.
Yes.
And here, this is rather like when I curve that piece of paper, and suddenly it becomes much stronger, much stiffer because of the shape.
Yes.
And this then is a double curve.
Yes.
So, well, simply speaking, you've got twice the effect.
It's got twice the effect. In this case, you've only got the increase in strength in one direction. Here, you've got an increase in two directions.
And it's not just eggs that have curves in all the right places. In 1902, the egg's shape inspired an American engineer, Gardner Stewart Williams, to build the world's first double-curved dam.
Usually, dams are built a bit like this. Well, not exactly like this. It's not a dam, it's an art installation. But the point is, traditionally, dams are narrower at the top, growing bigger and wider towards the bottom, using sheer size and bulk to hold back the weight of a man-made lake.
Concrete dams often have one curve, like arches, but tipped on their side. As the water presses against the curve, the pressure is spread along it. The combination of sheer size and the arch shape holds back the water. But it takes a lot of concrete to build. Still, for strength, one curve is good, but two curves are better. Williams realized this when he designed a radical new type of dam in Ithaca, New York State. His new cupola dam needed far less material because making it double curved meant it could be much thinner but just as strong. Williams designed his dam to be 27 meters high and just 2.5 meters thick. That's less than half the thickness of a traditional arch dam of that height. Very thin indeed.
So narrow, in fact, that locals were so worried it might burst, they insisted construction was halted at 1/3 of its planned height.
Although it only reached 9 meters high, Williams's dam still holds back water in Ithaca. And his double-curved idea continues to be used in dams today. But just how strong is a double curve? Is it enough for these eggs to take the weight of an entire car?
Are you happy it's lined up?
A modification.
I've already modified the car. It's important, that's why we've got to adjust the whole thing now that the car is lowered down flat onto the eggs, because obviously if it goes down one side or the other first, then all the weight will be focused on just a few eggs. We need to spread it amongst all of us. See, there's more science to this than you'd think. It's a precise thing.
Ah, good lad, though. There we go.
This is just eggs. They're not hard-boiled, as the chicken provided them. Away we go. This could get messy if it doesn't work.
It could. And we're right in the firing line.
Yeah, well, you worked it out. You said you could do it.
3/4 of a ton of car versus some eggshell.
It's so messy.
Oh, I can hear some...
I can
hear cracking.
Is that it?
I think it's worked,
I
Victor.
always said it would. I always said it would.
There are only chicken eggs holding up a whole car.
Now, in actual fact, you worked it out. You reckon that those eggs could hold more than that?
I think so, yeah.
What I'm getting at is I've got another crushed car.
The eggs are supporting 3/4 of a ton already, but could the double curved shape let them hold more? Can they take a second car?
This is going to be the fun part.
You'll hear them say things like left a bit, right a bit. Precision.
Yeah. Oh, I can hear cracking again.
I can hear cracking.
Some rather intriguing cracks I can hear now.
These eggs have delivered. I mean, they really have. That's 2 cars. I think we've proved the point.
Thanks to their double curve, these eggs are supporting over 1.5 tons.
One final thing, just in case you thought, yeah, hang on, they're all hard-boiled eggs or made out of concrete, I'd just like to prove they are all real, raw eggs. Amy, are you ready?
Yep.
OK, line up your wire.
Uh-huh.
A bit closer, a bit closer, a bit closer. Are you happy?
Yep.
OK, right, let's go. 1, 2, 3, go! Yep. Definitely real eggs. Stronger than you think, and all thanks to that shape, the double curve. And like dams, eggs, and boats, the walls here at the Guggenheim are built with a double curve to give them their strength.
But the double curves created a whole new problem. Normally, architects make scale models and then draw 2-dimensional plans, which the engineers build from. But the Guggenheim's contours are so complicated, it would need thousands of these plans, a nearly impossible task. Gary turned to something that would allow them to build it without all those plans: computer-aided design, or CAD.
It's hard to believe now, but until Gary came along, 3D computer-aided design had only been used on cars and planes.
Some architects had used rudimentary CAD before, but the Guggenheim was the first time it became an essential part of the entire design and construction process.
This was an architectural revolution.
Once Gary had designed the building using wooden and cardboard models, he turned to software created for engineering fighter jets. To use the advanced software, first Gary's models needed to be entered into the computer. This meant measuring them precisely. And that isn't easy on such abstract shapes. Traditional methods like rulers and calipers were too slow and impractical to map the unusual shapes. Gary needed a way to measure quickly in 3 dimensions.
And the solution to his problem began with the humble trundle wheel. You'll have seen these, surveyors use them to measure distances. 1 full revolution of this wheel takes me 1 metre along the ground. Simple. And they used exactly the same principle to design the world's first tracker ball.
So the trundle wheel can measure in one direction or axis. The next stage is measuring in two axes. It's the job of the tracker ball, which is basically an upside-down computer mouse.
Here's how it works. This is the ball that you move around. And whilst you're moving it, what it's doing is turning these little miniature trundle wheels inside. The engineers call them rotary encoders, probably because it sounds cooler. But that's essentially what they are, trundle wheels turning.
As the ball moves, so do the mini trundle wheels. One measures movement in one direction along the x-axis, the other at right angles to it along the y-axis. So both coordinates can be recorded simultaneously. It was invented by a group of engineers just after the Second World War as part of a Canadian project called DATAR, a way of sharing radar information between ships. The tracker ball was used to move a cursor across the radar screen to the position of the ship. When the operator pressed a button, the exact coordinates of the ship were recorded instantly. DATAR was too expensive to go into full operation, but its principle went on to inspire the invention of the computer mouse.
It was these rotary encoders that made it possible to measure accurately and quickly in 2D. All well and good. But for Guggenheim, Gary needed something that would work on his 3D models.
Without it, Gary's futuristic building could never realistically be built. But luckily, in the 1970s, an American engineer called Homer Eaton found a way of easily measuring in 3 dimensions, all thanks to his passion for pipes.
Homer started making exhaust for hot rods as a high school hobby. And, well, this isn't a hot rod, obviously, it's a standard car. But you can see, even on a standard car like this, the exhaust is a bit of a 3D puzzle because it's got to make left and right turns and up and down. Homer needed a way to replicate the bends and turns he made for a particular design every time. He needed a device to measure precisely the left and right turns, the ups and downs he put in the pipe. What it needed was a 3D measuring device.
So Homer invented one. He used the tracker ball idea and added more rotary encoders so it could measure in all 3 axes. Homer had invented the snappily titled articulated measuring arm. It was just what Gary's team needed to scan his Guggenheim models. Homer's arm is still used today, and measuring expert Steve Schickel is here to show me how it works.
So am I overstating it to say that this is a kind of modernised version of what Homer Eaton came up with?
The principles of this are exactly the same.
So how do you then use it?
It's like pointing your finger, so you take it to the surface, I just put it on the surface, push a button, and I get an XYZ coordinate. It's as simple as that.
Gary's team used Homer's measuring arm to painstakingly enter every individual point needed to scan his models. Even making an accurate computer model of a small shape like this takes at least 2,000 coordinates. Nowadays, laser scanners do the same job much quicker.
Steve, this suddenly looks faintly sinister. What is it?
What we have here is a scanning CAD.
Can you demonstrate?
Would you like to take a seat?
You know, I saw the scene and thought, yeah, go on, all right, I'll take a seat, yes. You're going to scan my face with that?
Exactly.
OK, begin. It's like visiting a very futuristic dentist.
As Steve scans the laser over me, it measures the distance to my face. At the same time, the tracker unit, that's the thing that looks like a slightly sinister robot, is measuring the position of the laser using rotary encoders. All the information is processed by a computer to produce exact X, Y, Z coordinates.
OK, Richard, you can now open your eyes.
You're done?
I'm done.
Right, so where is it now? Where's all that data?
Hopefully you can recognise the person that's on the screen.
It's disappointing. Is this machine very accurate?
It certainly is.
Oh, God.
We're getting down to about 30 microns, which is half the thickness of a strand of hair.
So that's all stored now in this computer as data?
That's right. If you actually look on the screen, we just show this as points. Each one of those is a single XYZ coordinate.
Steve took thousands of coordinates in less than a minute. In the same time, Gary's team would struggle to take 60 in making their computer plans. Those plans could then be manipulated by the software, but Gary wanted real models to play with, so the process was reversed at every stage.
Gary's team would continually make new models for him using the coordinates on the computer system. They were usually in wood and took a lot of time to make. Nowadays, 3D printing allows fast reproductions of just about anything, including my face.
Thanks to the humble trundle wheel, engineers could start building Gary's wild curved shapes. And I get a see-through mask of my own face, which will come in very handy if I ever want to pretend to be myself. But once the museum's skeleton was built, there was a new problem. What should cover the steel frame and clad the building? Gary wanted something that looked alive. But when the Guggenheim was built in the 1990s, Bilbao was a port city with a highly polluted atmosphere.
What material would give the shimmering, breathing feel that Gary wanted, but still be robust enough to withstand Bilbao's corrosive atmosphere? For the answer, the architects looked to a Russian submarine.
Rewind to the Cold War, behind the Iron Curtain. The Russians had a secret weapon that put them leagues ahead of the Americans under the sea: titanium. It's one of the most common metals on Earth, but it's hard to extract from ore and equally hard to work. But the Russians persevered and pioneered its use to make submarine hulls.
It is amazing stuff, titanium, because it is so light and so strong for its weight, which is what makes it ideal for making high-performance cars as well as submarines, and for cladding a building like the Guggenheim.
Titanium is as strong as steel, but much lighter, so the Russian subs could operate faster and deeper than the Americans. But just how much better is titanium? I've got a great idea for finding out.
I'm going to do something I've always wanted to have a go at. A bit of safe blowing. But I am going to need some space and a few friends.
One simple, short experiment can show the comparative advantages of titanium over steel with ease and a small explosion.
It's a sturdy thing, isn't it?
The safe has been reinforced with 6 millimeters of steel, and inside it is 12 grams of explosive, which will produce the same pressure as a submarine feels 100 meters under the sea. Explosives expert Mark Skuse is here to make sure I don't go bang with it. First, I'm going to see how steel copes with the pressure, so I've replaced the door with a thin steel plate.
Now, this, of course, is an unusual piece of safe blowing compared to the norm because we had to actually open the safe to put the explosive charge in it and then close it. We've put a steel door on the front. Are we done?
We're done. You want to take the igniter wire?
Ah, right. Can this go bang now?
No, it can't go bang.
Will these glasses protect me if it does?
OK, this is the box of tricks. OK, if you want to turn the system on, make sure everybody's well back out the way.
If everybody wants to get back and be safe, please. It will avoid a lot of paperwork.
With the explosion rigged and my helpers at a safe distance, it falls to me to do the honours.
3, 2, 1.
OK, results for the steel door pretty clear.
Look at that. Clearly. Oh, but it's gone. It's gone. Where's it gone?
No idea.
The door's gone. It's gone. It's just blown clean off. Yeah, I think that's what we've done there, is expose perhaps the limitation of steel in this particular application. So what we need to do now is gather everything up, tidy up, and get set to do this again with the titanium door.
The team rigged the safe exactly as before. Same charge, same safe. The only difference is the door. This time, it's made from titanium.
This is actually the best job, and they've given it to me as a sign of respect.
And to make it a fair comparison, I've used the same weight of titanium as I did steel.
3, 2, 1.
Lots of smoke in the air, but not much cash.
So, that was contained within a steel safe. are explosive, which means a tremendous pressure on the titanium door, and it was only about this thick, and it's fine. Look at that. That is pretty strong stuff, and it's not a complicated demonstration. It's fairly simple. We just blew a safe with titanium on the front of it, but really to see it graphically demonstrated like that, that's some strong stuff. Well, I don't think this could be any clearer, could it, really? Equal weight of metals, titanium and steel, equal charge, 12 grams of flash powder in both instances. The titanium bowed out a bit, but held strong. The steel, we found 20 metres away, shredded. So there's no doubt, titanium, light and very strong. But that's not all the Russians noticed about it.
They knew it didn't corrode, making it perfect for protecting their subs from seawater and the Guggenheim from pollution. Titanium reacts easily with oxygen to form a thin surface layer of titanium oxide. Once there, this layer stops it from corroding.
But the Russian sailors had noticed another peculiar effect. The oxide layer had caused the titanium on their submarines to change colour. One lot called their sub the Golden Fish. Might not be a useful feature on a war machine, but perfect when it comes to coating an art gallery.
For Gary, this effect meant titanium was the only choice to finish his masterpiece. Fernando Perez is one of the architects who worked with him.
We explored a number of different materials. Stainless steel with different finishes, very shiny. Aluminum, too flat, not alive. One day, Gary's people came with one idea. Okay, we've brought a sample of titanium. What? We thought, oh my God, these guys are crazy.
What did titanium do when you brought a piece of it down here and looked at it? Why did you think, yes, let's use that?
The main thing is that the material is alive, unlike any of the other samples we had. Then suddenly this material reflects light in a completely different way.
The effect of this surface is remarkable. It looks like thousands of fish scales, and then you only have to start moving, and it all looks like it's changing colour. It is stunning.
It happens because titanium reflects light in an unusual way, the same way as bubbles do.
White light, as we all know, is made up of lots of different colours. All the colours of the rainbow, that's where they come from. And when it strikes either a bubble or the titanium surface of the Guggenheim, some of it is reflected back straight away off the skin. That's the oxide layer in the case of the museum. Some of it is reflected from further down, and those different reflections can interfere with one another.
Some light reflects from the outside surface of the bubble. Some passes through to the inner surface and is reflected from there. When the two reflected beams cross paths, some light gets cancelled out. And if you take away some light from white light, you see coloured light instead.
Where I can see yellow on the surface of the bubble or the museum, the blue wavelengths are being cancelled out. Where I see green, the magenta wavelengths are being cancelled out, and so on. It is really rather beautiful and can be used to great artistic effect.
Chemist Lynn Bartlett uses the effect to make coloured titanium jewellery. She's going to show me how the reaction with oxygen forms different colours.
Once it hits the air, there's a thin layer of oxide on the surface. If you want to colour, you thicken that oxide layer.
So it's all to do with this oxide layer?
Yeah.
How do we thicken it on the surface?
Well, there are two ways, really. You can use heat and electricity. So,
Right.
Shall we start with heat?
Yes, let's start with heat. What do we do?
Right. One propane torch. And you can see...
Oh, it's not sophisticated, this. You're just going to heat it?
Just heat it,
Okay.
yeah.
Well, look at that.
The heat from the blowtorch gives the titanium energy, which it uses to bind with oxygen from the air to make titanium oxide. The more heat it gets, the thicker the oxide layer that forms.
Well, can I have a go?
obviously.
Of course.
Is that all right? Seriously? If I wanted to make the whole thing blue, I heat it until I get an oxide layer of sufficient thickness to make blue. Oh, there it is, there it is, there it is.
Yeah.
So it's quite a beautiful effect.
Just like on a bubble, the reflections from the titanium oxide cross paths and cancel out some colours. Which colours are cancelled depends on how thick the titanium oxide is. So this swirly pattern is created because the oxide layer is all different thicknesses.
But obviously there's nothing like this happening on the Guggenheim, because it would look rather gaudy, covered in little swirly circles.
It would, Rob. Now, if you want an overall effect, anodising is the way to do it.
And that's what this is. It's a fish tank.
It's a fish tank full of an electrolyte, which provides the oxygen.
And what we're looking for is a more uniform effect rather than the little swirls that were happening.
Yes,
Okay.
yes.
Anodizing works in a similar way to heating. You give the titanium energy and it makes titanium oxide. But this time the energy comes from electricity and the oxygen comes from the solution in the fish tank, not from the air. It's a more controlled way of thickening the titanium oxide layer and gives a more uniform result. But it is a very slow process on this basic equipment.
Paint, dry.
To make the oxide layer thicker, you turn up the electricity. Each different voltage gives a different thickness of oxide, and so a different coloured stripe.
Can I take it out now? Can I touch this yet?
The power is off, so it's safe to
Can I trust you? Do you want to go first?
Absolutely.
Right, so let me just have a look. Each of these different coloured layers, so that results in a different thickness of the oxide layer on top of the titanium itself, and that's done by controlling the voltage that you're putting through it.
Each one, yes, yes.
The thinnest oxide layer gives a pale gold colour that Gary loved, and it's also protective. So thanks to a Russian submarine, the Guggenheim will glisten in Bilbao for years to come.
Using titanium tiles gave Frank Gehry the magical look he wanted, but it also gave him an additional problem. In fact, pinning them to the steel structure gave him 264,000 additional problems. That'll be the 264,000 holes made by screwing them in place, each hole ready to let in water. Not what you want on a gallery filled with precious art. Bilbao's winters are renowned for being wet. On average, 1.2 metres of rain falls here a year. That's twice as much as falls on London. So how are the engineers going to make their building waterproof? The search for a solution takes us on a trip with Sir Walter Raleigh on his quest for El Dorado.
The year is 1595. Sir Walter Raleigh and his fleet of Elizabethan explorers have crossed the Atlantic on the hunt for El Dorado, the mythical land of gold.
His fleet is damaged and leaking. Limping round the Caribbean, he reaches Trinidad. And here, he makes an important discovery. The largest natural lake of bitumen in the world, the Pitch Lake of La Brea. Now, this is probably the first time Sir Walter's seen bitumen, but he has the sense to use it to seal his ships and waterproof his fleet.
Walter Raleigh used a crude, natural form of bitumen to seal his ships. For the Guggenheim, a slightly more refined version was needed. Unlike Sir Walter Raleigh, Dr. Ian Lancaster is a bitumen expert.
So, Ian, this is it then, the raw stuff in its basic form. You see, it looks like, to be honest, something that I'd spread on my toast. But it's not, is it?
Wouldn't do you much good.
But it has some amazing properties.
It's viscoelastic, incredibly adhesive, and it's 100% waterproof.
OK, now the waterproof I get,
Yeah.
adhesive I get is sticky. Viscoelastic.
Changes its properties according to both temperature and the rate of strain.
OK.
So if you look at sample here, this is a soft bitumen,
So why can't you then just paint a layer of this onto the top of the museum? Job done.
It flows. You wouldn't want to do that because it would
just
flow.
fall off.
The soft bitumen would have been no use on the Guggenheim. It would have simply slipped off the curved structure.
But there are some other grades of bitumen which are quite hard.
Melt it like that and then paint that on, and then you've got a hard shell.
That's fine at high temperature. At low temperature, this gets incredibly brittle.
So,
Have a go with that.
OK, so we'll just hit it.
Just hit it. Look at that.
That really is quite brittle, isn't it? That's
It is.
clearly going to be no use once it's cooled on the roof.
No.
This bitumen is similar to the pitch Sir Walter found at La Brea. OK for a ship, but no good for the Guggenheim. Once it sets, it would just crack and split as the tiles were screwed on. It wouldn't be very waterproof with cracks in it. They needed bitumen with something added to make it more flexible. Rubber.
This is a rubber modified one, and that gives it a concept called elastic recovery. Have a
So
pull
when
of
you
that.
say rubber modified, well, hang on, it feels so light. Wow!
It goes a long way.
Now, there's no way we could have done that with the other stuff.
No.
And then it's just returning to its original shape.
It'll go right back to its original shape. And when you think about it, on the roof of the Guggenheim, 264,000 screws go through this, puncturing it all the time.
Surely, to me, that just says, well, then water will get through the hole and it's no longer serving a purpose.
No, because as the screw goes in, the bitumen deforms and then it pulls back, so it wraps around the screw, making it completely watertight.
So even though they screw through this stuff, it actually sort of heals itself around it.
Yeah.
Because it returns to its original shape and that it's still waterproof.
Yeah, it self-heals.
So by adding rubber to the pitch Raleigh found in Trinidad, they've made the perfect raincoat for the Guggenheim.
This is a titanium tile. Each one is folded over on the edges like this, so it hooks into the one above and below it. Beneath the tile is this, the steel layer. And between the steel and the titanium is this, the bitumen waterproof layer. And that's the secret, because when these brackets holding the tiles in place are screwed through, 264,000 of these screws, it's the bitumen layer that self-seals around it and stops them leaking. And it must work, because they've never found a leak.
Well, that's what they told me, and I hope they're right, because I'm going to test it out myself in the middle of a lake.
You may have noticed that I'm sitting in a rubber dinghy in the middle of a lake, and you may, a bit like me, be wondering why. Well, I've devised a little test taking some inspiration from Sir Walter Raleigh and this nail.
The Guggenheim's engineers tested the waterproof membrane using a wind tunnel and some extreme rain, but I've got a different plan.
I've coated the bottom of my dinghy with the same membrane used on the Guggenheim, and I really am hoping it does self-seal and form a protective layer because, well, it's just a few drops of rain against the Guggenheim. Here, it's me and this dinghy against 6 meters of water below. Still, what could possibly go wrong? The equipment is not complicated. Hammer, nail. Put nail through dinghy. Not something I'd advise anyone else to try on a lake, but... I'm standing by for a huge gush of water to sink my boat, and nothing. I could sort of feel it as I forced the nail through. I could feel it seal around it. And there isn't, I would have expected just a dribble of water to come in around the edge where it's split, but I think probably the best thing to do with the experiment now is repeat it, because I have many nails. Well, she's certainly not sinking. All I've got to do now is get back, maybe have a look underneath. And it's me power for that.
"33,000 square meters of the Guggenheim were covered in the same bitumen rubber compound that's under my dinghy. And so far, it's kept millions of pounds worth of art perfectly dry.
I'm out. just want to see where the membrane's done its stuff. And there it is. You can see how it's sort of healed right around the nail, which is why it didn't leak a drop into my boat. So, Sir Walter Raleigh, a lake of bitumen and the amazing properties of rubber work together to help keep the Guggenheim's artworks protected from the elements.
But it's not just the weather that could prove disastrous for the Guggenheim. Being largely constructed of meltable steel, a fire would be catastrophic if it ever took hold. To solve this problem, the architects looked at the fieriest place on the surface of the Earth: a volcano.
Fire always poses the biggest threat in public buildings, and obviously the public safety is paramount. But in an art gallery like this one, well, there are irreplaceable objects everywhere. The art. And you really should try and save that.
The gallery has traditional sprinkler systems placed throughout, but they're only designed to cope with small, isolated fires.
But what if a fire took hold? Obviously, the people will have been evacuated and hopefully most of the artworks, but the heat of a raging fire can be devastating to a building because once steel reaches over 600 degrees, it loses half its load-carrying capacity. So the engineers needed something that would stop the Guggenheim collapsing.
To find out what they came up with means going somewhere most people never get to see, inside the museum's walls.
Thank you. And now let me guess. Up the big ladder. And then I'm guessing it gets worse. I just know it will. OK, up the big ladder. It is remarkable how many fascinating engineering connections are also very high up. Really big ladder. Nobody ever does any fascinating engineering near the ground. Always got to be high.
Fires in buildings can rage at over 1,000 degrees C and last for hours. Engineers needed a way of protecting the steel skeleton from the intense heat so the Guggenheim doesn't collapse, destroying millions of pounds worth of art.
For the solution, the engineers turned to nature and used a naturally occurring fire-retardant substance that can withstand temperatures of over 1,000 degrees. And it's this, mineral wool. It's made from volcanic rock, and mixed with concrete, it sticks very nicely to the steel structure of the building, which should protect it from the heat, stop it from melting, and the building from collapsing.
This connection takes us back to 19th century Hawaii, where scientists studying the volcano Kilauea found strange threads of glass scattered around. During violent eruptions, lava is spun into glass fibers like candy floss. The tresses are called Pele's hair, after the volcano goddess who Hawaiians traditionally believe lives inside Kilauea. Combining these fibers created a fantastic insulator, mineral wool. It should protect the steel skeleton of the Guggenheim for up to 4 hours, hopefully enough time to quash the blaze. To see if it's up to the job, I've built a wall out of steel panels. They're protected with mineral wool on one side. At the Guggenheim, they sprayed it onto the steel girders, but I'm using easy-to-handle sheets, and in front of those is fire.
So this is a proximity suit? Yes. That sounds quite space age. I like the sound of that.
It's aluminiumised to reflect the heat away from you. Perhaps in the same way that you'd wrap the top of your chicken in aluminium foil in the oven to stop it burning.
I'm oven ready, is that what you're saying?
Basically.
I like it, but it's a bit 70s disco.
Apparently, I'm the only one that needs a disco suit because they aren't going that close.
I'm guessing right now it's something out of Doctor Who, circa 1960. Very nice. This is tremendous. Right, the idea of this is I'm going to be experimenting with fire, taking temperatures and things. You guys are looking after me. How will I know if it's not working, the suit?
As soon as you start to feel mildly uncomfortable, then it's time just to walk away.
Walk?
So no.
Okay. Right, well, I've got one piece of kit here. Right, there's work to be done. Over there.
I almost wish I hadn't added this little baby into the mix now. It's a propane-powered flamethrower and it burns at well over 1,000 degrees C, hot enough for steel to fail structurally and me to roast. Let's hope the suit works better than it looks.
Right. Well, I have my 2 safety fire officers, and I have a thermocouple thermometer here, so I can actually get a good idea of how hot it is in this incredibly hot flame.
The thermal imaging camera shows me where the hottest part of the flame is, so I can get right in there with my probe.
Right now it's 17.5 degrees. As I get closer, leading in with this probe, 35, 44, ooh, all of a sudden, 121 degrees, that's 198, 320, 407 degrees, 582, 600, that's the temperature which already steel will have lost half of its load carrying capacity, 989, that's 1,000, it's 1,100. Well, that's both too much for the probe and for me, so let's retreat.
The hottest part of the wall is over 1,100 degrees C. That's around the temperature building fires burn at, and well over the temperature at which steel begins to fail. Now I'm going to see what it's like behind the protective layer of mineral wool.
OK, well, science and other people's experience tells me I should now be fine to go on the other side of the huge roaring flame without my special suit. So let's have a look and see how it's doing its job. I notice you two are still wearing your special suits. Good, good. Now this is telling me the temperature here, 29 degrees. Don't forget, just the other side of that wall is that fire that was raging at, well, over 1,100 degrees. 28 degrees is the sort of ambient temperature. It's actually getting cooler as I get closer because I'm shielded by it. 27 degrees. So technically that means I could touch it. Can I touch it?
Yeah.
I wish they'd said no. OK. Yeah, absolutely fine. So we know it works. Question now is how. Now,
Nick Ralph knows all about mineral wool.
OK, so I've now experienced very much firsthand it at work. Clearly, it does work. How?
Well, we're all familiar with insulation in the form of a woolly jumper. The principle is that there are small pockets of air trapped within the material which prevents the heat travelling from one side to the other.
The air will stay trapped as long as the fibres don't melt, which they won't do because they've already survived much, much hotter temperatures inside the volcano. They can easily withstand the temperatures of building fires.
So this basically is about the gaps in between these fibres, and they're stopping it conducting the heat through. And it's as simple as that.
It is as simple as that. Obviously, the difference here is that normally when we wear a woolly jumper or we insulate our homes, we're trying to keep the heat in. And in this instance, what we're trying to do is keep the fire out.
Well, clearly, it does work because I stood, well, that far from 1,100 degrees C and wasn't in any way influenced by it. So the art at the Guggenheim is safe.
Thanks to a volcano and some goddess hair, the Guggenheim and its priceless art is protected from fiery destruction.
So if it wasn't for some pretty clever engineering, the Guggenheim Museum in Bilbao wouldn't be the world-class, iconic gallery it is.
And the clever engineering is all because of an egg, a trundle wheel, a Soviet submarine, Sir Walter Raleigh, and an Hawaiian volcano.
All you need are the right connections.
BBC Two's in Africa for the next chunk of tonight, Botswana with the Top Gear boys next, and then Mali, Ghana and Nigeria are on Jonathan Dimbleby's itinerary in a brand new series at 9. And for those of you who are glued to the tennis, Murray's match has resumed and is over on the red button.